Good morning, everybody. Hope everyone had a nice weekend. We're going to work on equilibrium today. We have a challenge question to start with. We'll run through equilibrium, and tomorrow we'll do what's called Le Chatelier's principle, and that'll finish up the unit. And then the plan is to have the unit test on Wednesday from 9 to 10:30. So let's go ahead and get started. So I want to do the challenge question from the other day. Describe the factors that affect reaction rate. There are 5 of them. First one was nature of reactants. Second one we talked about was the concentration. And under concentration, there was a special one for gases, and that was changes in pressure. Third one we talked about was temperature. The fourth one was surface area. And finally, the fifth factor was adding a catalyst. So those are our 5 factors that you should know that affect reaction rate. Next one. Write a balanced chemical equation for the formation of ammonia gas, including the heat term. As soon as you see heat term, they're talking about the delta H, which means we're going to have to use table I. So if we go to table I, hopefully you know what ammonia is now. So ammonia is NH3. So we come over here and we got to scan down until we find NH3. Here's the equation. So we can go ahead and copy that down. 2N2 gas plus 3H2 gas goes to 2NH3 gas. And the delta H that's listed is negative 91.8 kilojoules. Now, hopefully you realize now that we don't have a negative energy. There's no such thing as negative energy. Right? The negative energy is just telling us if this is exothermic or endo. And the negative sign tells us that it's exothermic, which means heat's released or produced. It's a product. So to put this in here, we just write plus 91.3 kilojoules. And this would be my equation with the heat term. Good. So let's go ahead and get into equilibrium. Now, you guys have all heard about equilibrium, or the word equilibrium before. If you took bio last year, if you're a junior, you talked about the human body and its equilibrium, and that's called homeostasis. So what is equilibrium? Well, it's a state of balance between the rates of 2 opposite processes that are occurring, OCCURI, at the same time. The B part of this. The equilibrium must be in a closed system. What's a closed system? Well, a closed system means nothing can get in, nothing can get out. So in a closed system, nothing is gained or lost from the system. So it's a state of balance between 2 opposite processes that are occurring at the same time. And you can say in the same container if you want. and it must be a closed system. So those are two things that we need to get this equilibrium. Now, there are two types of equilibriums. There are physical equilibriums and there are chemical equilibriums. And we're going to run through some of the physical equilibriums, and then we'll eventually talk about a chemical equilibrium. So let's start with physical equilibriums. We're talking about physical equilibriums. We're talking about phase changes, mostly. Phase changes and dissolving are two things that we're talking about when we're talking about physical equilibriums. So let's talk about a phase change equilibrium. Okay, so phase change equilibriums occur when we're going from a solid to a liquid, or liquid to a solid. So this is during phase change, when we're melting and freezing. So remember when we talked about this thing? We said temperature doesn't change here. Well, this is where equilibrium is in this phase change. So if we're right here, all right, we have solid and we have liquid. If we add heat, okay, more of this is going to melt. But if we take heat away, more of it's going to freeze. So this is actually at an equilibrium. You can also have a liquid gas equilibrium. You can have a liquid gas equilibrium. And that would be the same thing up here. So let's say that I'm right here. Right here I have both phases. If I add heat, it's going to push it towards the gas side. If we take heat away, it's going to push it down here to the liquid side. Now, before we go any further, I should probably talk about these double arrow things. So the double arrow things, and let's kind of just do it over here. The double arrows, we'll just do it down here. We'll do it down here. These mean that it's at equilibrium. And both the forward and reverse processes are occurring. Okay. That's what this double arrow means. Now you'll see the double arrow drawn lots of ways. This is one way. You could see it this way. Fancy ways, you might see it like this. You might see it like this. I think that's all. I think. Now, how do I draw it usually? I usually draw it like this. Sometimes I'll quickly do it like this. So these are the two that you'll see for me, but you'll see all of these, and they all mean the same thing. It means that it's at equilibrium. All right, good. So now that we understand that, let's go back and talk about our phase change equilibriums again. So we said equilibrium is when we have two opposite processes. Now, do we have two opposite processes here? Well, if we're going that way, we're melting. And if we're going the other way, we're freezing. Those are two opposite processes, okay? So we have two opposite processes. Now, I actually want to go through and draw this one when we're going from liquid to gas. We again have two opposite processes. Okay, going to the right, we have boiling. Okay, going to the left, we have condensation. Those are two opposite processes. So I want to draw this one. H2O, liquid, in equilibrium with H2O gas. So the first thing we need is we need some H2O liquid and some H2O gas. So let's draw an Erlenmeyer flask. And let's dump some water in there. And we're going to put this over on the counter and we're going to let it sit. And what happens? Well, over time, some of these water molecules at the surface will have enough energy to break away from the surface and become water vapor. And then another one will break away from the surface and become water vapor. All right, it'll evaporate. And another one will break away from the surface and it'll become water vapor. Now, what do these particles do? Well, they're gas particles, so they vibrate, rotate, and translate, and they translate in constant random straight line motion. So you go boom, 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 boom. Will this ever reach equilibrium? Well, over time, what's going to happen? More of this water will evaporate, and it's going to go down, 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 down. Eventually, all the water will have evaporated, all right, and there won't be any water left. This will never reach equilibrium. Why? It is not a closed system. It will never reach equilibrium. It will never reach equilibrium. We're losing water vapor, so this system is open. It's called an open system. All right. Well, how do we make this a closed system? Well, what if we stick a cork in it? So what I want to do is I want to draw it again. And here's my water. And this time, I make it a closed system by putting a cork in here. So nothing can get out. So we cork it. Now we let it sit. And again, some of these particles will give enough energy and it'll break away from the surface and become a gas. Then another one will break away from the surface and become a gas. And another one will break away from the surface and become a gas. Another one will break from the surface, become a gas, get a gas, becomes a gas, becomes a gas. Now, if we set this aside and we come back later, I don't know, maybe tomorrow, what do we start to see? We start to see condensation here on the sides of the container. Where's that condensation coming from? Well, that water condensation, some of this water vapor loses energy and clumps back together and becomes a liquid. So some of these guys start to condense back into a liquid. And some of these condense back into a liquid. But at the same time, we have gas particles coming up here and becoming a gas. And then another gas particle becomes a liquid. And then a liquid particle becomes a gas. And we start to get this cycle going on inside the container. Now, this will reach equilibrium. Now, what's equal at equilibrium? It's not the amounts of stuff. It's not the amount of water and the amount of water vapor. The rate of the opposite processes is what's equal. So in this system, when we reach equilibrium, the rate of evaporation is equal to the rate of condensation. It's really important that you understand that the rates are what's equal at equilibrium. Now, what is that actually saying? Well, what it means is this. It means that the rate of evaporation, so every single time, let's say, 2 of these come up, If the rate of evaporation and condensation are equal, that means two of these are going to go down. If one of them comes up, one comes down at the same time. If five go up, five go down. So at equilibrium, the rate of evaporation, or the number of gas particles, liquid particles becoming a gas, is equal to the number of gas particles becoming a liquid. Now, once this reaches equilibrium, what do we know about the amounts of liquid water and gaseous water? Well, if every time one of these comes up, one of these comes down, that means the amount of this and the amount of this doesn't change anymore. The amounts are constant. So at equilibrium, the amounts of H2O liquid and H2O gas are constant. They don't change anymore. What's equal? The rate of evaporation is equal to the rate of condensation. The amounts are constant. They don't change anymore. Right, so this is an example of a physical equilibrium. This is the equilibrium between liquid and gas. We could draw the same thing out with a solid and liquid one. So we could make an ice water bath. Okay, and it's the same thing. Eventually would reach equilibrium. Some of the ice would be turning into liquid, and at the same time, some of the liquid would be turning into ice. So we could actually draw the same thing, right? But it's the same exact idea. So we have phase equilibriums, and then our second physical equilibrium is called solution equilibrium. Now, solution equilibriums, remember, if we have a solution and it's at equilibrium, that means it's at saturation. The solution is saturated. So if we use table, is it table G? No, I was right. Okay. So remember this table? Right, so remember, if we're on the line, it's a saturated solution, and that means it's at equilibrium. So when we're talking about solution equilibriums, we're talking about dissolving ionics into solutions usually. So the solution equilibrium I want to talk about today is NaCl solid in equilibrium, okay, in water with Na pluses aqueous and Cl minus aqueous. Now, what's happening here is we have two processes happening again. Okay, we have dissolving happening, so we have a solid dissolving into our solution, and at the same time the reverse process is happening, and we're taking two ions and they are solidifying into NaCl solid. So these again are opposite processes, and we need to be able to draw this. So what I want to do is I want to draw, let's make an Erlenmeyer flask. And I'm going to fill it with water. Okay, so we're full of water. And then we're going to add some salt. And we add some salt, and we stir it around, and it dissolves, and we form Na pluses and Cl minuses. And then we put some more salt in there, and we get some more Na pluses and some Cl minuses. And we add more salt, and we get Na pluses and Cl minuses. We add more salt, we get Na pluses and Cl minuses. We add more salt, we get more Na pluses and Cl minuses. And eventually we get to a point where it won't dissolve anymore. It's reached saturation. So if I put more salt in there, where does it go? Well, it won't dissolve, and we get this salt on the bottom. So this is some solid salt down here. So this solution is saturated. Down here we have NaCl solid, right here. Now, what do we have to do next? Is this a closed system? The answer is no. So what we need to do is we need to close it. So let's put a cork in it. Now we have our closed system. Now, I wish I had this, or I wish I had you at school, because I actually have this at school, and it's really, really, really cool. Once we reach saturation, this equation keeps happening. You can't see it happening, all right, but it keeps happening. So NaCl is going to keep dissolving into the water. But at the same time, an Na and a Cl are going to come and precipitate out and become a solid. And in my flask at school, you can't see the process, but you can see the results. And we'll talk about that in a minute. So our two processes that are happening here are dissolving and crystallizing, or solidifying. So those are two opposite processes. Now, once this is saturated, what happens is one of these NaCl particles will dissolve and become Na plus and Cl minus. But at the exact same time, if this is at equilibrium, an Na and a Cl will come together and form NaCl solid. And then another one of these will dissolve and become Na plus and Cl minus. But at the same exact time, an Na and a Cl will come back together and form NaCl solid. At saturation, if this is at equilibrium, what's equal? Well, remember, it's the rates of the processes that are equal. So at equilibrium, in the solution equilibrium, the rate of dissolving is equal to the rate of crystallization or precipitation, or whatever you want to say. Remember, it's the rates that are equal at equilibrium. So this is at equilibrium. Now, once this has reached equilibrium, what do we know about the amount of NaCl solid and the amount of Na pluses and the amount of Cl minuses? Are they equal? Chances are no, okay? That's not what's equal at equilibrium. But what do we know about these things? Well, if every time one of these comes up, two of these come down, okay, every time we have an NaCl break apart and become an Na plus and a Cl minus at the exact same time, and Na plus and a Cl minus come together. So the amount of NaCl salt is constant, the amount of Na plus in the solution is constant, and the amount of Cl minus is also constant. So at equilibrium, the amounts of NaCl solid, Na plus aqueous, and Cl minus aqueous are constant. The amounts don't change. Now, what's cool in my beaker at school is this. You can't see this happening, but it is happening. So in my Erlenmeyer at school, it's been running for about, I think I made it my second year of teaching. So it's been running for about 16 years. Now, how big are salt crystals, like from your salt shaker? Well, they're tiny, 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 right? You can see them, but they're tiny. I use regular table salt inside my Erlenmeyer. But if you look inside it, the salt crystals are actually really, really, really big. And what happens over time is the small ones dissolve into the solution. And when they crystallize on top of each other. So these crystals keep getting bigger and bigger and bigger and bigger and bigger and bigger and bigger on the bottom here. So you can see the result of this equilibrium. You can't see it happening, but you can see that it's happening because we have salt crystals getting bigger, and the little ones keep dissolving in here. Right? It's pretty cool. If we get back to school, I will show it to you. Okay, it's actually pretty. All right, this is solution equilibrium. So our two physical equilibriums are phase change equilibriums and solution equilibriums. Now I want to talk about what happens in a chemical equilibrium. So what we're going to do is I'm going to actually take you through how a chemical equilibrium develops. Right. So what we're going to do is we're going to look at this reaction, and it's a general reaction. A plus B, or AB plus CD is going to end up producing an equilibrium between AD and CB. This is the equilibrium that we're going to look at. Now, what we're going to do is we're going to take it in parts. Step 1. When the reactants are first mixed. So we originally take our AB and our CD and we put them together. Right at the instant that this starts. Well, at the very instant this starts, do we have any of the product yet? No, we don't have any product. There's no product. All of it is AB and CD. Now, at the very instant that we put these together, the concentration of AB and CD is very high. The concentration is very high. Now, what did we say about reaction rate if the concentration is high? Well, if there's lots and lots and lots of this, there's going to be lots and lots and lots of collisions, so the reaction rate is going to be fast. So the forward reaction rate is very fast. What about the reverse reaction rate? What about going that way? Is there any reverse reaction happening right here at the very beginning? Well, the answer is no. There's no product. So there is no reverse reaction. So the reverse reaction rate is 0. Are we at equilibrium? No. Why? Well, if we're at equilibrium, these have to be the same. Now, let's let this run a little bit. So we let the reaction happen. So we have some AB, it reacts with CD, and it's going to produce a little bit of AD and CB. Now, as soon as we have some product, what can start to happen? As soon as we have AD and CB, the reverse reaction can start to happen. So we start to get both reactions happening in the same container. So this, let's write this right here, as the reaction progresses. Let's not use that color. So now, as this reaction happens, what happens to the amount of A, B, and CD? Well, the A, B, and CD are reacting together to form product. So the amounts of this is decreasing. So the concentration of the reactants is decreasing. What's happening to the concentration of my products? Well, we're making more and more and more and more of it, so the concentration of this guy is increasing. Are we at equilibrium? Well, we have to look at the rates. What is the forward reaction rate doing? Well, remember what we said about concentration. Okay, the more concentrated it is, the faster it goes. But the concentration is slowly going down. It's decreasing. So what's happening to my forward reaction rate? My forward reaction rate is decreasing. What about my reverse reaction rate? Well, my reverse reaction rate is increasing. So we're making more and more and more of this. So my concentration goes up. As my concentration increases, there are more collisions, and the reverse reaction rate also increases. Are we at equilibrium here? Not yet. We are not at equilibrium yet. Okay, so what does it look like at equilibrium? So let's go back to this. So this one, the reaction rate is starting really, really high, and it's slowly coming down. The reverse reaction rate starting really down here, and it's increasing. So this one's coming down, this one's coming up, down, down, up, up, down, up, down, up, and eventually they get to the same exact rate. The rate of the forward is going to be equal to the rate of the reverse. When they meet, we reach equilibrium. And that's what happens here. So once we reach equilibrium, what that's saying is that every time an A, B, and a C, D to come together to form these guys, at the exact same time, one of these guys comes together to form these guys. So the concentration of this one is constant. And the concentration of the products is constant. So once we reach equilibrium, the rate of the forward reaction is equal to the, should be an E, rate of the reverse reaction. I realize this has to be happening in a closed system, so it's got to be in a closed container, so nothing can be gained or lost. So we get this rate of the forward is equal to the rate of the reverse. Now, what's constant at equilibrium? The amounts of stuff is what's constant. So the amounts of reactant and product are not equal, but they are constant. They don't change anymore at equilibrium. And this is what a chemical equilibrium is. Now, there are some graphs that you need to be able to recognize with equilibriums. And I want to run through them with you. So I want to draw 3 small graphs right here real quick. 1, 2, 3. And I want to label it reaction rate And down here, we're going to label it time. Forward reaction, reverse reaction, and both reactions. Now, I'm going to use two different colors. I'm going to use orange for my forward reaction. So for my forward reaction, where did the rate start? Well, the rate started really, really, really high. It started way up here. And then it slowly went down, 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 until it leveled off, and the rate stayed constant. All right. What did my reverse reaction do? Well, it started at 0. There was none. And it went up, 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 and then it levels off. Well, what does this look like together? Well, let's draw it. We started high, it comes down, it levels off. And this one started at 0. Now, where on this graph does it reach equilibrium? Well, where the rates are equal is where it reaches equilibrium. So by this graph, where they touch, somewhere right in there, this is where it has reached equilibrium. This is when we have reaction rate and time. Reaction rate and time. Where they overlap, okay, we've reached equilibrium. Now, what the Regents likes to do is they'll throw this at you too. There are two more graphs that I want to draw. Except this time, we're going to label it amounts of reactant and product in grams and time. So instead of reaction rate, we're talking about amounts of reactant and product. Same thing here, amounts of reactant and product in grams and time. So I'm going to say this color is reactant. And I'm going to say, let's use blue. This color is product. Well, over time, what happens to the amount of reactant? Well, it starts high. And then eventually it levels off. What does the amount of product do? Well, it starts at 0. Then it levels off. Has this reached equilibrium? And where? It has reached equilibrium. Okay. It's not here. It's not where they touch because the amounts are still changing. What did we say about the amounts at equilibrium? They are constant. So where on this graph does it stop changing? Somewhere in here, where these amounts are constant, it reaches equilibrium. Well, let me draw another graph. Same thing, okay? This is my reactants. Starts high. Has this system reached equilibrium? And the answer is yes. They don't have to touch. Remember, at equilibrium, the amounts are constant. They're not equal. They are constant. So where do they no longer change? Well, if we look at the graph, probably, I don't know, a guesstimation is somewhere in here. They don't change anymore. So this is where it has reached equilibrium. Be very careful with these types of questions on the exam. You have to decide, am I looking at reaction rate versus time or amounts during time, amounts versus time. If it's reaction rate, you reach equilibrium where they touch. If it's amounts, it's where they're constant. So just be very careful with this. Okay, I have two little things to talk about, and then we are done for today. I need to mention something about table F. Okay, and this is our solubility tables. And we've used these. So it's this one right here. And we've used these, and we were able to predict some reactions with this. And we said that if one or more products are insoluble, a reaction would occur. Well, there's an additional thing to that. If an insoluble precipitate forms during a reaction, the reaction will never reach equilibrium. So for example, Be parentheses NO3 2 aqueous plus Na2CrO4 aqueous goes to BeCrO4 and 2NaNO3. So if we look at this reaction and we go to table F and we look these up, we find that Na is a group 1. Group 1s are always soluble. So this would dissolve and be an aqueous. And if we look at chromates, they are usually insoluble unless it's with a group 1, calcium, magnesium, or ammonium. Well, it's with beryllium, so it's not one of these. So this actually is a precipitate. So this reaction happens. This reaction happens, but it will never reach equilibrium. And the reason why is there is no reverse reaction. If it produces a precipitate, there is no reverse reaction. The BaCrO4 will never react with the NaNO3 to produce these guys. Since there is no reverse reactions, the rates can't be equal. So there's no equilibrium. Every once in a while that pops up on the Regents exam. And then the last thing I just want to remind you, because this one pops up a lot. Remember table G. That's our solubility table. Where are we at equilibrium? If a solution is saturated, it is at equilibrium. All right, make sure you remember this one because that pops up quite a bit. All right, that's all we have for equilibrium. All right, we have just Le Chatelier's principle left for tomorrow, which isn't bad, and we'll actually do a worksheet together. And we're almost ready for a unit test. All right, hope you have a great afternoon. Bye.